Hello students, good morning. Today we start with the second partial, and the name of the topic of the first topic of the second partial is freefall. Okay. To begin with freefall, you have to remember something about the last partial, and as I told you on the last partial, the kinematic equations are some of the equations that we are going to continue using, but this time they are going to have a change. This change is going to be that we are going to add something here. Instead of calling them in the same way, now we are going to use something like this. As you can see, instead of final velocity, we are going to call it only final velocity on y. That means on the vertical, because we are talking about free fall, vertical plane. The VO, VOY. The acceleration is acceleration on y, and the time, as you can see, the time remains the same. Okay, then instead of x, we are going to use y. Instead of VO, VOY, the t remains the same. Instead of acceleration, acceleration on y, and so on. Okay, so as you can see, we have the same three kinematic equations that I think that you know them already. So the only different thing is like that, and that we are going to be using a specific acceleration. This specific acceleration is going to be an acceleration that is due to gravity. Okay, so the gravity that we are going to be using, or the acceleration due to gravity that we are going to be using, is this one, minus 90.8 meters per square second, that some people also called it gravity only, okay, but it's the acceleration, okay. That's why we use meters per square second, okay, and we use the minus because we are talking about an acceleration that is trying to pull the object down, to pull the object to the ground, okay. Perfect. So with this information, we're going to be able to start. You can open your manual if you want, ClassWork 13, and I am going to help you with the first problem, and I'm going to solve another problem after that one. With that information, you're going to be able to solve all ClassWork 13. Okay, so let's start. First exercise on ClassWork 13. It says something like this. The tour demon drop in the amusement park Cedar Point falls freely for 1.5 seconds beginning from rest. What is its final velocity after this time, and how far down? So let's start writing down the values that the problem is telling us. Okay, the first value that we have is that it falls freely for 1.5 seconds. So let's write that one. Okay, we have that the time is 1.5 seconds. We're good on that. Now, it says that it's from rest. Do you remember that when we have something like from rest, means that at the beginning here, the beginning of the fall, you are not moving, you don't have velocity. So that means that your initial velocity will be 0. But this time, instead of VO only, it's the VOY, the one that is 0. Okay, VOY. Why? Because we are talking only on the vertical plane. Okay, so it's the initial velocity on the vertical plane, on y. Perfect. And the extra value that we have here is the acceleration. The acceleration is going to be always the same because it's the acceleration due to gravity on Earth. Okay, and because we are on Earth, all the problems that we are using on Earth are going to be with the same value, that is minus 9.8 meters per square second. Okay, so we have three values here. In a similar way as the problems that we were solving on the first partial, we have three values here. Okay, and we need to choose an equation, one of these three equations of the kinematic equations. So remember that I told you before that you have to see what do you have and what do you want. Okay, we have time we have initial velocity on y, and we have the acceleration on y. And we want, it says, what is its final velocity. Okay, so as you can see, if we check this tree, we are going to see that we have the VOY, we have the time, and we have the acceleration, and we want the final velocity. So the first equation is the one that we are going to use to solve it. So let's check. If we replace values, we're going to have that the initial velocity is 0. Okay, we have it here. The acceleration, it's minus 9.8, negative. Pay attention to that sign, okay, because it's going to be always negative. Okay, and the time, that is 1.5 seconds. So this 0 doesn't count. The minus 9.8 multiplied by 1.5 is going to give you minus 14.7 meters per second. Okay, and as you can see, this is negative. But why negative? Well, it's negative because the velocity is used as a vector. So always that the velocity is moving down, you are going to have a negative velocity. If the velocity is moving up, you are going to have a positive velocity. Okay, this is something important to check because we are going to have this same kind of problems in the manual. Okay, so negative, and this is negative because of the sign of the acceleration, and it's negative because it's moving down, so it's correct, minus 14. Perfect. Next question, how far down? So it's asking about the position or the distance that is moving, right? Okay, perfect. So what do we have? Well, we want the y, right? Because the y is like the x that we have in the last problems, in the last partial. So my y is like the distance, but talking about the vertical distance, and my y over here. So I have to check what values do I have and which values do I want. In this case, I'm gonna choose this one because as you can see, we have the time, we have the acceleration, and we have the initial velocity, and we want to get the y. Okay, so the only thing that you have to do is replace values. Let's check. Instead of initial, 0. Instead of time, 1.5 seconds. Instead of acceleration, minus 9.8. Instead of the time again, 1.5. And then you solve this one. As you can see, this goes, and you have only the 9.8 divided by 2, that is minus 4.9, multiplied by the square of 1.5, that is 2.25. When you solve this equation, you're going to have that your y is minus 11.025 meters. But once again, you're going to say, well, why do we have a negative value here? Well, this is something very important, and check this. You started from here, you started from the maximum value, the maximum height of your demon drop, okay? And you drop, like it says, drop some people going down, right? So in this point, you have to imagine that you have like a Cartesian plane, okay? A Cartesian plane like this one, okay? And you're gonna take you're gonna imagine that the y is like the position, okay? In the moment that you begin, in the moment that you drop your object, that's gonna be your 0, okay? That's your Cartesian plane. Your Cartesian plane is gonna be on 0, okay? If you move up, you're going to have a positive value on your y, okay? If you move down, you're going to have a negative value on your y in the same way as the velocity, okay? So velocity and y are going to be talking, or are going to be using as vectors. You are going to have positive or negative values depending if you move up or if you move down. And you have to take in consideration that the moment that you start the problem, that you drop your object or that you throw your object, in that moment, that is your 0 position of your Cartesian plane, and beginning from that point, If you move down, you begin counting your distance, okay? Or if you move up, you begin counting your distance in a positive way, okay? So according to that, if I move from the start and I move down, I am going to have that I have a distance of 11.025, but negative because we are moving down. Okay, that is the first problem. The second problem is not in the manual. Okay, this problem is a little bit more difficult. Let's check it. This problem is not in the manual, this is on a book. Okay, but I want to explain this one because if you know how to solve this kind of problems, you're gonna be able to solve any problem related. Okay, so let's check it. We have the kinematic equations again here, and we have the problem like this. It says, a ball is thrown from the top of a building with an initial velocity of 20 meters per second strike upward. Okay, so as you can see, a ball is thrown upward, okay, over here. The ball just misses the edge of the roof and its way down. So it doesn't matter that it's only telling you that it's not gonna touch the building. Here it's gonna continue going down until the ground. Okay. As shown in figure 220, this one. Determine the time needed for the ball to reach its maximum height. Here. Okay. The maximum height, that one. The time needed for the ball to return to the height from which it was thrown, and the velocity of the ball at that instant. In this instant, when you throw the ball and then goes down again in this moment. And the time needed for the ball to reach the ground over here. Okay, let's start. First, what values do we have? It says that we have an initial velocity of 20 meters per second. Okay, so we can start with that. Initial velocity on y, b of y, of 20 meters per second. Positive because it's moving up, right? You are throwing the object up, so you have a velocity of 20 meters per second positives. Perfect. Now we have an initial height of 50 meters above the ground, so it's telling you this distance. But this distance in this moment is not important, and I'm going to show you why on the last letter that we have here. Okay, so we have the initial velocity on y, that is 20 meters per second. It says determine the time needed for the ball to reach its maximum height. We want to know the time from that since you throw the ball until the maximum point. Okay, something important here is that you have a value that is going to be in all these kind of problems, and is the acceleration. The acceleration, as I told you before, is the acceleration due to gravity because you are on Earth. So this acceleration is the same that I told you before, minus 9.8 meters per square second. But we need another value so we can solve it. So we can choose one of these three kinematic equations that we have. And that value, this is something important because it's something that you are going to apply in similar problems to this. Check this. If you throw something, you're going to have a velocity that is, each time that you are moving up, the velocity is smaller, right? And when you get to the maximum point, you stop there, and then you begin accelerating again, but in a negative way. Okay, but when I say that you stop in the maximum point, I'm referring that if you stop, that means that you don't have velocity, right? And if we are analyzing the problem like this the beginning and this that we have here the end, I have initial velocity 20 and my final velocity, that is the ball in the maximum point and is the ball that is stopped, that will be 0. So my final velocity on y in the maximum point is going to be 0. Why? because the ball stops here in the maximum point. When I say stops, is that you don't have velocity, right? Okay. Now with that explanation, you have the three values that you needed, so you can choose one of these three kinematic equations. What do you want? According to the problem, you want the time needed for the ball to reach its maximum height. Okay, so we want time, and we have initial, final, and acceleration. As you can see, initial, final, acceleration, and we want time, so the first equation is the one that we can use here, right? Okay, so the only thing that you have to do is isolate the time from this equation, leave the time alone, like this. Okay, and then replace the values that you have. You know that the final velocity on y from here to here, this is your final velocity, and on this analysis, okay, it's 0, according to what I explained before. The initial is going to be always 20, because that's the initial, and the acceleration is going to be always minus 9.8. Okay, so when you solve this one, you're going to have a positive value of 2.04 seconds, the time. So that means that the time that you spend from here, or the ball spends from here to here, it's 2.04 seconds. Okay, that's the first answer. Perfect. Now, B, the maximum height. Right now, you know what is the initial velocity, you know what is the acceleration due to gravity, you know what is the position, well, the final velocity that is 0 and the maximum point, and you know the time that you spend to get from here to here. Okay, so you can use all that information to express it. Okay, so you have these four values right now. Now let's take the second equation. Why the second equation? Because you have time, you have acceleration, you have initial velocity, and you want the y, you want the height, the maximum height, right? Okay, so the only thing that you have to do is replace values here. Replacing the initial velocity, 20, in the time, 2.04, in the acceleration, minus 9.8, in the time, 2.04 again, but it's squared this time. Okay, and you're going to have something like this, 20 multiplied by 2.04, 40.8. Minus 9.8 divided by 2, minus 4.9, and as you can see, I am placing this minus over here, and 2.04 squared is 4.62. Multiply these two, and you get 20.38, sorry, and then 40.8 minus 20.38, you're going to have at 20.42 meters. Okay, so as you can see, the 20.42 meters is not the distance, or is not the maximum height from here to here. Okay, it's not from the ground to the maximum point. It's from the point that you begin to the maximum point. Why? Because as I told you on the last problem, imagine that you have a Cartesian plane over here, okay, and that is your 0. In talking about the vertical position where you start, that is your 0, okay, and beginning from that point, you moved 20.42 meters up. That's why you have a positive 20.42 meters. Okay, so that's the answer on B. Let's check C. For C, we have what is the time needed for the ball to return to the height from which it was thrown, and the velocity at that instant. So it's talking about, you have to tell me what is the time when you throw the ball and then the ball is going down again in the same point, in this point, in the same height of the height that you had when you started the problem. Okay, so you want to know the time at all this time from here to here and then again here. Okay, and you want to know the velocity at that point. This is easy, but it's more logic than equations. Of course that you can use equations, but I recommend you use some logic here. When you have problems like this, the time that the ball or the object lasts to get from here to the maximum point, and from that point again to the same vertical point is gonna be always the same. What is the meaning of that? Is that the time that you are doing to get from here to here up is exactly the same time to get from here to this point up down. Okay, so the only thing that you have to do is multiply that time by 2 or add 2.04 plus 2.04. Okay, and that's gonna be 4.08 seconds. One more time. This is because the time that you do on moving from here, from the initial point to any point, and then from that point to the same point in the vertical plane that you were before, is exact. The time from here to here and the time from here to here is exactly the same. Okay, so you add them or you multiply it by 2 and you have the time. Okay, perfect. So 4.08 seconds. Now, what is the velocity on this point? This is also with logic. Of course that you can use also the same equations, but I recommend you use the logic a little bit. The velocity that you have on this point is going to be the same velocity that you have on this point, but in opposite direction. Okay, so if you are throwing an object with 20 meters per second up here on this point, when it's moving down, you are going to have 20 meters per second, but this time negative. Okay, why? Because it's on the same point, in the same y, on the same vertical point. Okay, so this is gonna be something that is gonna happen always like that. Okay, so now we have C. The time 4.08 seconds to move from here to here, and the velocity there, that is the same as the initial but negative because it's moving down. Okay, D, the time needed for the ball to reach the ground. Okay, right now we know the initial velocity, that is 20 meters per second, and it's the same in all the problem because it's initial. We know the acceleration, that is the same acceleration because it's due to the gravity on Earth, minus 9.8, and we need something else. Check this. That something else that we need could be the distance that we have from, well, we are talking about the ground, right? It says the time needed for the ball to reach the ground, to reach this point. And we know the distance from this point, from the ground, to the initial point. We know that distance is here, is 50. But if you remember about what I told you about the Cartesian plane, you're going to remember that if this is your starting point and you are moving down from that initial point, that means that you're moving in a negative direction. That's going to be a negative sign that you need to use. And that negative distance that you're moving is 50. So it's minus 50. One more time. Why? Because you're starting from 0 and you're moving down. And remember that y is talking about position, and that always the initial point that when you throw the object, that's your 0, and beginning from that point, you will start counting. It could be positive if you move up or negative if you move down. So now we have 3 balls. And we want to know what is the time to get here. Okay. There are a lot of ways of solving this kind of problem, but I'm going to explain you one that it could be easier. Okay. Because in this point you can use equation 2, because you have y, you have initial velocity, you have acceleration, and you need the time. But as you can see in this equation, the times are separated. So if you choose that equation, you're gonna need the general formula. Okay, to use the general formula, and I think that you don't have to get to that point right now because we are studying right now. Okay, so what do you have to do, or what can you do if you want to do it in an easier way? Well, you can also use the third equation. Okay, in the third equation we have the initial, we have the acceleration, and we have the y. So, but you are going to calculate the final velocity, right? Okay, don't worry. You calculate first the final velocity, and then with that final velocity, you calculate the time. Let's check. Applying this equation and replacing the values, I have got the initial velocity that is 20 squared plus 2 times the acceleration that is minus 9.8 multiplied by the position on y, or the vertical distance from the initial point to this one, that is minus 50. You're gonna have that is something like this, and as you can see, we have a positive value here because it's minus positive, right? You add them, and you're gonna have that is a square root of 1380. But remember that when you work with a square root, that is the value that you got from the square root could be positive or negative, depending on your problem. In this case, we're going to choose the negative value of this one. Why? Well, once again, because the final velocity that we have is a velocity that is moving down, right? Here, when you are here, before you touch the ground, your final velocity is moving down, right? So you have a negative velocity. Okay, if your velocity is moving up, like the initial, is positive, but if your velocity is moving down, it's negative. So we have that. And with this value of the final velocity, we can calculate the time using the first kinematic equation, this one. But the only thing that you have to do is isolate the time. Okay, so when you isolate the time in this way, now you replace values. Minus 37.15 minus 20, that is the initial, divided by minus 9.8, that is the acceleration due to gravity. And from the subtraction that you have in the numerator, you have minus 57.15 divided by the acceleration. You're going to have that the time is 5.83 seconds. So the time from getting from here to here all this way until you get to the ground is going to be 5.83 seconds. Okay, perfect. So with these problems that I explained here, you're going to be able to solve ClassWork 13. Let me check. And this is here. This is ClassWork 13. As you can see, we already solved the first exercise. In the second problem, the only thing that I have to tell you is that the CGS system is only working with centimeters and seconds instead of meters and seconds. Okay, so that's why you have the answers with centimeters per second and centimeters. Okay. And remember this, when they say dropped, the meaning of that is at the beginning you don't have velocity. Okay, perfect. And you have the time here, and you have the acceleration due to gravity of the earth. Okay, perfect. In this one, only remember that the 46 meters is 46 meters that are moving down. So this is similar to the problem that I explained, the first problem that I explained. This is not positive. This is a y that is not positive. It's negative. Okay. And you have to express this in the English system. That's why you have feet per second and second. In the next problem, as you can see, you have imagine that you have 3 different problems in one. You have 4 different problems in one. And the meaning of this is that you work now with meters and seconds. MKS is that meters per second, seconds and seconds. Okay, this one is also a body is dropped. It's similar in the English system. And this one, a body is thrown vertically upward. As you can see, this is a little bit similar to the second problem that I explained, but this one is a little bit easier. By the way, on exercise 5 and exercise 6, the acceleration is not minus 9.8. Okay, the acceleration on the moon is 1.6 meters per square second. That's the acceleration on the moon. Okay. Of course, that you have to pay attention here that you are not working, well, that you are working in the English system. You have to change that meters per square second to feet per square second when you work with it. Okay, and that's all. These are 6 problems. So the homework for the next class is going to be to finish them, and with this explanation, I think that will be enough to it. So see you next class. Have a nice day, and I hope that you don't have a lot of problems trying to solve this classwork. Okay? See ya.